Okay, everybody, so welcome back. So we have a couple more topics to talk about in Chapter 1 before we're done with this material. When I'm done with the Chapter 1 material, which I should finish by the end of lecture tomorrow, what I'm going to do is have, so like Wednesday's lecture will basically be just a review of that stuff, where I'll do a bunch of examples. And then that'll be that. Then we'll move on to Chapter 2. So like I said, I have two more things. One thing is, so this is our first run-in with what are called numerical methods. So the idea behind numerical methods is you have a differential equation. Maybe it looks something like this. So for the numerical methods section, I believe the assumption is that you have an equation that looks like this, and here's, maybe it's an IVP, so you have some initial condition here. Okay, so here's the differential equation in question. Notice the way that this is written. This is a very, very general equation. That big F can be anything, say, continuous, right? That's continuously differentiable with respect to y. So this big F can be pretty much anything, which means that this need not be separable, definitely need not be linear. So, so this is a very, very general first order ODE. Now, we're not going to be explicitly solving it. The point of numerical methods is to come up with a numerical solution at, say, a given value that is a numerical approximation of the thing, right? So explicitly solving it gives you a closed form expression. Y of t is equal to blah, is equal to some function of t, and you can just explicitly plug in, whatever thing you want. A numerical method seeks to come up with a numerical approximation to the value of the solution at any point. Of course, there's a lot to that. So if this is, sometimes you have a differential equation that cannot be explicitly solved using any method learned in this class or otherwise, and so it could only be numerically approximated. In other cases, of course, you could apply this numerical method to any of the problems that we've actually been able to do, and hopefully, right, this would be close to what you obtain by explicitly solving it. In this way, you can kind of calibrate, you can get an idea of how close this thing is. And otherwise, you could, maybe you see, oh, well, actually, this numerical solution is suggesting that the solution is actually this simple thing that I didn't consider, right? Of course, for us, linear and separable, we know how to do those things, so those are good ways of checking our work here. So there are a number of numerical methods to talk about. There's the Euler method. So for the Euler method, there's two different types of Euler method. There's what's called the explicit Euler method and implicit Euler method, or backwards Euler method. I'm really only going to focus on the explicit Euler method. So, and I'm typically not even going to call it that. I'm just going to call it Euler's method. So this is called explicit or forward Euler method. All right. So there's Runge-Kutta. There are a few things. There's when MATLAB solves some of these differential equations. So there's a solver known as ODE 45 or 45, I guess is probably a better way of calling it. I'm not going to get really into those or what MATLAB is doing when it comes to those things. This is going to be the one that we focus on the most. But if you're interested in that stuff, this is covered in 1.7. So all this is in Chapter 1, Section 7, numerical methods. It talks about Runge-Kutta. It talks about some other things, but we are going to focus on Euler method. So what is the goal, right? So the goal is to estimate the value of the solution y at some t value. I'll call it like t star for now. So I want to estimate this thing, okay? All right, and I'm going to do this in a way that does not require me to actually solve this differential equation. If I could solve the differential equation, I wouldn't need a numerical solution, or I wouldn't need a numerical approximation to the value of solution. So it's very important that this method not actually require me to solve the thing, right? Okay, so rather than go through kind of the derivation of this, or justification for what it is that's going on here, and to kind of to stress, it's not so complicated actually what's going on here. Basically, what I do is use the definition of derivative, like the limit definition of derivative, and just merely interpret what it is that's going on. Maybe I should do that, because this is essentially what is done. In fact, you may have, like, this might suggest like echoes of Calc 1 Newton's method stuff. So the idea is on the left-hand side, if I'm looking at what the actual definition of this is, this on the left-hand side, this is the derivative of y t, so this is the limit as h goes to 0 of y of t plus h minus y of t over h. Right? That is my dy dt, which is big F of ty. So another way of saying, you know, what this is if h, which is positive, is very small, very close to 0, what this is saying is that y of t plus h minus y of t over h is approximately equal to big F ty. Right. And so, moving this over to the other side, this means if h is small, so if I multiply both sides by h here, I get y of t plus h minus y of t is approximately equal to h times big F of ty, which is my right-hand side function. I add that to the other side, and so this means that y of t plus h is approximately equal to y of t plus h big F of ty. This actually does it. Okay, this tells me what is going on here. So let me rewrite my equation. So my equation is dy dt is some big F of ty. That's my differential equation. My initial condition is y of t sub I is equal to y sub I. Okay. And so what is the idea here? I want to use this fact to come up with an algorithm that approximates values of y using this relationship. So I could say, right, let h be some positive quantity that I typically think of as small, right? So typically thought of as small. Now, what does small mean? Well, you know, obviously small depends on the problem in question or what you're considering small, but in some sense it is small, and the reason for that is so that this relationship holds, right? This came directly from the limit definition of derivative. Okay, so it's typically thought of as small. Let, say, t naught be defined to be this t sub I, this initial value. Okay. Then t sub 1 is defined to be t naught, which is the initial t value, incremented by h. So I take my initial time value and I increment by h. H is thought of as the step here. This is the step size. So in my next time step, I have incremented the previous time step, my initial time step, by h. Okay. Now, these are the time values. Corresponding to these, there are y values. So y naught is defined to be y of t naught. Okay. And y sub 1 is defined to be y of t sub 1. Continuing on here, if I go up to the n plus first time step, how did I obtain the n plus first time step? Well, I obtained that from the nth time step by adding or incrementing it by h. So that similarly, y sub n plus 1 is defined to be y of t sub n plus 1. Okay, now we're ready to actually state the expression that gives you this algorithm, okay, in a nice form. So just using this fact here, so for instance, let's put in the nth time step on the right-hand side. And so on the right-hand side, I have y of t sub n plus h times f of t sub n, y sub n. Keep in mind here, y sub n is y of t sub n. Okay. This is approximately equal to what, according to this? Well, it's approximately equal to y of t sub n plus h. But t sub n plus h is t sub n plus 1, so this is approximately equal to y of t sub n plus 1. Okay. So this is it. This is Euler's method, or explicit Euler's method. Like I said, I'm not really going to distinguish because this is going to be the only one that we talk about, really. Okay. So there it is. Okay. What does this tell me? This gives me a way of estimating the value of y at the n plus first time step in terms of the nth time step. So this is a recursive, definition here where I can build this up from the initial time and the initial value. I can build up, right? I can increment by h over and over and over again. This gives me my various time steps, and I can estimate the value of my solution at each of those time steps just from this. And notice, what does this take? I don't need to solve the differential equation. All I need to do is to be able to do this algebra, right? I don't even have to take a derivative. I don't have to do any of that. I just have to plug in these values here, right? So this is a very, very simple, very simple method. It's actually surprising for how simple this is, how nice it can be. So for some differential equations, this is going to converge nicely and quickly. And this is actually going to provide a really, really good numerical approximation for the solution, despite being as simple as it is. Okay, so let's see how this works. All right, so I'm going to rewrite Euler's method at the top of the next page. So Euler's method, here it is. So rewritten in a shorter way, this is y sub n plus 1 is approximately equal to y sub n plus h times big F of t sub n y sub n. Okay, this is the shorthand method of writing it. Y, let's just remind ourselves here. Y of t sub n is defined, or t sub n plus 1 is defined to be y sub n plus 1, just like y sub n is defined to be y of t sub n, right? And then the rest is obvious. Okay, so here's Euler's method. Let's do an example of how this works. Once you've seen one of these examples, you've pretty much seen all of them, because you're going to be doing these by hand. You will be implementing Euler's method using MATLAB in one of the MATLABs later. But you know, if you're asked to do this like on a homework or on an exam, you're going to be what should I say? You're going to be doing this by hand, and so you know these are not going to be like, you're not going to have to do this to 10 time steps. You're not going to have to do a ton of like nasty basic arithmetic or anything. It's just going to be a few steps just to illustrate you know what's going on. So here's an example. So let big Y of t, we'll say, be the solution of the initial value problem. It's dy dt is equal to t squared plus y squared. And with initial condition y of 0 is equal to 1. Okay, use the explicit Euler method to approximate y of 0.2. Now, typically this would give you some freedom in how you would do this, because you would be allowed to pick the step size. But let's say that I give you the step size here, right? So use the explicit Euler method with h is equal to 0.1 to approximate y of 0.2. Okay. So here's my differential equation. Now I need to, you know, identify what form this is in so that I can actually apply this Euler's method formula here. So what do I have? dy dt is equal to big F of t is this thing. So in this example, big F of ty is equal to t squared plus y squared. Okay. And in this example, t naught is equal to 0, right? Y naught, which is y of t naught, is equal to 1. And h is equal to 0.1. So now I have all quantities that I need to get this process rolling, right? So a couple of things, I might as well go ahead and work some of these out. So if t naught is 0, then t sub 1 is t naught plus h, but then this is 0 plus 0.1, which is 0.1. Okay. Y naught is 1. H is 0.1. We have everything we need in order to approximate y sub 1. By Euler's method, y sub 1, which again, remember, this is y of t sub 1, right? So this is really y of t sub 1, is approximately y of t sub 0, which is y naught, plus h times f of t sub 0, y sub 0. So this is y naught, which is 1, plus h, which is 0.1, times f of t naught y naught. So this is t naught squared, that's 0 squared, plus y naught squared, which is 1 squared. So this is 1 plus 0.1 times 1, so this is 1.1. So we've said that y sub 1 is approximately 1.1. Now, for our purposes, we're just going to call this equal to 1.1 because we have to, so we're going to say y sub 1 here is equal to 1.1. Okay. You can see where we're going with this. What is t sub 2 here? Well, t sub 2 is t sub 1 plus h. T sub 1 is 0.1, so this is 0.1 plus 0.1. So this is 0.2. But this is the time value that we've been asked to approximate the solution y at, right? So we've been asked to approximate y at 0.2. All right, so then y sub 2, which is y of t sub 2, is approximately y sub 1 plus h times f of t sub 1 y sub 1. Y sub 1 we found to be 1.1 plus h, which is 0.1, times big F of t sub 1 y sub 1. So t sub 1 is 0.1, so this is 0.1 squared, plus y sub 1 is 1.1, so this is 1.1 squared. And if you work through this, so this turns out to be, at the end of the day, 1.222. But what did we say with this line? Y sub 2, which is y of t sub 2, that's y of 0.2, is approximately equal to 1.222, but that's exactly what we were asked to approximate. Thus, big Y of 0.2 is approximately 1.222. Okay. And so that's it. Now, there's something to be said here where if you needed to do this in a way that required you to use multiple time steps, like much more than 2, so say like 20 time steps or 100 time steps, clearly you're not going to do this by hand. You're going to do this by computer, okay? And this is a very easy to implement thing by computer, right? Once you have this is very, very easy to get going. So anyway, this is kind of a very nice representative example. It kind of shows what can happen here. Okay, so this is our numerical way of doing this. And again, notice what kind of equation was this? It was not linear, clearly, because this y squared term. It's not separable, right? So it's not linear, it's not separable. So currently in this course I have no way of dealing with this equation in any way. So if I want to get at what are some particular values of a solution, this is my only method, really. Okay, this is the only thing I can do. Okay, so that's all we're really going to touch on when it comes to numerical stuff for now. So that's pretty much it from this section. So just make sure that you know what's going on everywhere in this example, because any other example you come across is likely to be very similar here. Okay, so then I wanted to start what is the last topic in this this section. So here is the kind of the main topic in the very last. So if you look at the notes, if you look at the online notes, we have gone through all of the sections in order from the 0th section with some basic stuff So chapter 1, sections 1 through 7, that's what we just finished talking about with section 7. There's section 8, which is second order equations reducible to first order ones. That's not going to be something we focus on. That's an optional thing, and that won't make any sense to you really until you've seen some second order equations. So we're not gonna worry about that right now. Or I mean, it would make sense to you now, but it will make more sense to you later. But we're not going to worry about that one. So section 9 is the last one we're going to do. Section 10 is special equations and substitution. We're also not going to worry about that. That's an optional section. So it's so the relevant sections in chapter 1 are 1 through 7, and then section 9. Okay, and in a way, section 9 is probably the most involved, just because what needs to be done in order to solve these problems is the most complicated in terms of the computations you have to do, because there's a lot of steps to this process. Let's say I have a differential equation of the following form. Okay, now if I have a differential equation like this, where, so again, now x is my variable instead of t. Nothing wrong with that. So I have a differential equation like this. Okay, maybe I have an initial condition here just as well. So I have y of like x sub I is equal to y sub I. Okay, fine. Suppose, right, suppose I find that solutions to this equation are determined by an equation h of xy is equal to a constant for some function h. Okay. Okay. We've seen an example of this before. So what was an example we saw? When we had a separable equation, right? When we had a separable equation, sometimes we saw that we couldn't actually go further than some relationship that looked something like this, right? So we couldn't quite go the final step of finding an explicit solution, because in the separable equation process, the big G function that we got didn't have an inverse, right? It was not one-to-one. It just didn't have a well-defined inverse, and so what you ended up getting was that your solution was determined by some equation involving x and y, and there was this function h. Okay, so sometimes this is as good as you can get, but as I mentioned, we're actually relatively happy with that. Even if it's not an explicit solution, it still tells us a ton about what's going on. It's almost as good as having an explicit solution. In this case, we say h is an integral of the equation. I'll call it star. So this is my IVP. We would say this is an integral of the equation star, and I assume that h satisfies, the proper conditions to make this initial condition hold and all that stuff. Okay. So this is not the same as finding an explicit solution, okay, but we want to say that basically it is, okay? So we want to say that if a given equation has an integral, then for us, that is as good as considering this solved, okay? So having an integral is going to be as good as having a solution, because in a sense it's the same thing, right? Maybe I can't find an explicit solution, but it gives me some implicit relationship between y and x here, or y and t, if t is my variable, and that is going to make me very happy, because I can do all the things that I wanted to do in finding a solution anyway, right? So this is going to be us solving this. Now, why are we talking about this? Because we know that we can't always solve an equation like this. Look at how general this is. This is not necessarily separable. This is not necessarily linear. And so this is a more general type thing. We already know in the case of separable equations that we can't always find an explicit solution. So sometimes this is as good as we can do. The question is, when can we find such an h? In that case, we would call this differential equation integrable, or we'd say it has an integral. Okay. Well, there's a derivation that goes on here that I'm not going to go over, but from making some basic assumptions and taking some partial derivatives in the correct way, basically we can start here and derive sort of what sort of equation this should look like. Okay, and it turns out that we need big F of xy to be equal to minus m over xy over n over xy for functions m and n that are nice. That satisfy a certain property. Okay. So this is what we need. And if we want to guarantee that such an h can be found, they need to satisfy a certain property. Okay, so this is not always going to be done, or be able to be done for any f, definitely for any f, or even when f is of this form. Of course, you might say, wait, how do I know if f is of this form? What's going on here? Why is there a minus sign here? I will show the reason for this minus sign to make everything look nice. So let's write out our equation and claim that we're restricting our attention to equations that look like this, where m and n are some functions of x and y. Okay. Now, what I'm going to do is I'm going to treat this as I did previously, where I treat dy dx as an honest-to-God fraction. And so I can clear denominators here. And if I clear denominators, I end up with n xy dy is equal to minus m xy dx. And then I add this to the left-hand side. To get this expression. Okay. This is known as differential form. He doesn't say that in the textbook, but that's kind of what's implied here. So this is differential form. Okay. The reason for this, I won't get into too deeply. This thing on the left is what's called a differential form. What is a differential form? For now, you can just think about it like this. So these d's here, We're abusing notation a little bit, like I said, with Leibniz notation, but it turns out that it works out fine anyway. These d's are the same d's you can think of as showing up underneath an integral sign. Notice in an integral, right, like you never talk about the integral of a function without it having that d thing. So you integrate a function of t dt, a function of x dx. Right now, you might just think that that's like a notational thing that's just telling you what variable you're integrating with respect to. But really, it's kind of a fundamental thing, and it might blow your mind a little bit. Common thing to say is that functions don't have integrals. You can't integrate a function. It turns out that the only thing you can integrate is a differential form. What is a differential form? A differential form looks like, let me write it on a different sheet of paper. A differential form is something that looks like this. And it behaves differently from a function. It is f of x times this dx, and this thing transforms like a derivative. So this doesn't make any sense. Integrating a function makes no sense. This makes perfect sense. But this thing that you're integrating is not a function, it's a differential form. Okay. Now, if you want to know more about differential forms, you're going to have to take Math 437. That is basically what you spend the entire time talking about in Math 437's differential forms. But until then, we'll be content to just have these things floating around, and we don't really know, what's going on there, where we can just view them as notation, if you like. Okay, so the goal is to find h of xy such that h of xy equals constant is implicit solution to this equation. I'm going to go ahead and spoil the fun and say that this can't always be done. Note, this cannot always be done. But it can always be done if the equation, I'll call this 5-point star like this, if the equation is exact. What does exactness mean? Well, exactness means the following. So this is exact, so star is exact if and only if the y partial of m is equal to the x partial of n. So hopefully all of you have seen enough of Calc 3 to see partial derivatives. If not, then you'll get plenty of workout or plenty of practice in this section. Taking partial derivatives is the same as taking normal derivatives. You would just hold any other variable showing up as constant. You just pretend they're a constant and take the derivative like normal with respect to whatever thing you're taking the partial derivative of. Okay, so you'll see in a number of examples how this works if you haven't seen partial derivatives before. But anyway, this is what it means, that the y partial of m is equal to the x partial of n. Where does this condition come from? So I'm going to show you what we do, right? Or maybe I should say what we're going to do to construct this h. Okay, so the main idea is to let the x partial of h of xy. So maybe I should say let h of xy be such that the x partial of h of xy is equal to m. Right? The function showing up here on the dx. And the y partial of h of xy is n. We want h to solve these things simultaneously. Now, technically, this is like a system of partial differential equations, and this course is not about partial differential equations. But we'll see that the way we're going to treat it, this is not going to be an issue, because we're only going to treat one variable at a time. This may be bringing back memories. If you've had Calc 3 at UMD, this is something you do at the very beginning of chapter 15. So at the end material, chapter 15, when you talk about vector fields and trying to find a potential for a conservative vector field. This process that we're going to go through is going to look very, very familiar to you, because it's actually the exact same thing that's done in Calc 3 when you, like I said, when you first get to vector fields. Okay, so this is what we're going to do. Now, for a moment, right, I want to say, suppose that, like, this is our idea, and then our plan is solve this for h of xy, then h of xy equals constant, right, is the implicit solution to the equation. Our original equation, right? M dx plus n dy is equal to 0. So this is the idea. Another way of phrasing this is saying that h is an integral for this system. Okay, and so let's suppose that we've done this, though. So let's suppose we've already done this. Where does the exactness condition come from? Well, first of all, it's a fact of Calc 3 that if I take the y partial of the x partial of a function of two variables, x and y, that is nice, this should equal the x partial of the y partial of h of xy. Right? When you first were introduced to partial derivatives in Calc 3, one of the first kind of general properties that you talk about is the fact that it doesn't matter in what order you differentiate this thing, so long as the function is nice enough. Nice enough here just means it's continuously differentiable. So it needs to be continuously differentiable. If it's continuously differentiable at all of the points in its domain that you're in question, that's enough to guarantee that it doesn't matter in what order you do the derivatives, right? So you had to specifically cook up examples where this failed. And continuity was always an issue where that happened. So if you were dealing with something that was relatively nice, this was always true. Okay, and so that's our hope, is that this h is relatively nice, and so this is going to be true. In that case, then this has to hold. Okay, but if I'm claiming that the x partial of h is m, then on the right hand or on the left hand side, what I have is the y partial of m, and on the right hand side, I have the x partial of n, right? That's the exactness condition. So the exactness condition just arises from the fact that I want these partials to commute, right? So I want these partials I want them to be the same regardless of what order I do them in. So for that to occur, I need this exactness condition, okay? So that's what tells me that this h is nice. This is the thing that justifies why we would need this exactness condition, okay? So I think it makes sense to I think it makes sense to actually recast this or maybe I don't think it makes a whole lot of sense for me to go through this process in complete generality. It would serve no purpose. So I'm going to do some examples of our process here. Okay, so let's do some examples. So first example, dy dx plus e to the x y plus 2x over 2y plus e to the x is equal to 0. And we'll say that y of 0 is equal to 0. So solve this IVP. Now, maybe we're able to find an explicit solution. Okay, maybe not. Maybe we're only able to get an implicit solution. But either way, we'll consider that solving the differential equation here. How would I go about doing this? What kind of equation is this? It doesn't look separable, right? It doesn't look linear. So what is it that's going on here? Well, it's going to be some other type of equation, right? So hopefully it's of this type that we're talking about, and it's an exact differential form. So to see that, I need to rewrite it. So first of all, I can move this to both sides. I can move this expression to the other side. So dy dx is equal to minus e to the x y plus 2x over 2y plus e to the x. Clearing denominators if you like. What does this give me? And moving everything to the other side if need be. So this gives me e to the xy plus 2x dx, right, plus 2y plus e to the x dy is equal to 0. So there's my differential form. So then the thing multiplying dx, that's my m of xy. The thing multiplying dy is my n of xy. And the first thing I do to make sure that what I'm doing is going to have hope of working is I check the exactness condition. The way to remember the exactness condition quickly, it's going to be less of an issue for you all taking this online, but the way that you would remember this without having to look it up is to look at this and say, okay, m is the thing multiplying dx, so it's the y partial of m has to be equal to the x partial of n being the thing that multiplies dy. So it's the opposite variable in that way. So then the exactness condition, what is the y partial of m? So the y partial of m, I'm taking the derivative of this with respect to y, so I'm treating x as a constant. So treating x as a constant, the derivative of this with respect to y, the derivative of e to the x y with respect to y is e to the x. The derivative of 2x with respect to y is 0, so the y partial of m is e to the x. Okay, the x partial of n is the x partial of 2y is 0, because I'm treating y as a constant. The x partial of e to the x is e to the x. So the exactness condition holds, and there is hope that this process is going to terminate in a solution. Okay. All right. So then next, what do we set up? So next, we set up the equation. So set up equations del x of h of xy is equal to m, and del y of h of xy is equal to n. Okay, let's do that on the next page. So this is the system that we're setting up. So del x of h is m and del y of h is n. This is a system, so these are taken together. These both have to be satisfied simultaneously. All right, well, m, of course, is, let's bring this back for a second. M is e to the xy plus 2x, and n is 2y plus e to the x. So rewriting this, this is the x partial of h is equal to e to the xy plus 2x, and the y partial of h is 2y plus e to the x. So here's the part where you might recognize this from the end of Calc 3. Okay, because you did something extremely similar. I mean, not just similar, it's exactly the same thing. That's what you did. Okay, so, all right. There's my system of partial differential equations. So how do I deal with these? Because this is exact, this is going to work out very nicely. I can start with either of these equations I want. Of course, practically, you may want to start with the one that looks easier to you. In this case, they both look about the same. But really, functionally, it doesn't matter what you do here, but just pick one of them. Okay, so pick one. And if I pick one of these, so I'm going to pick the top here. What I do is I integrate both sides with respect to the variable in question to get rid of this partial derivative. Okay, and so this implies that h of xy is equal to the integral of the right-hand side with respect to h. So what's the integral of e to the xy with respect to h? Well, it's just e to the xy. What's the integral of 2x, sorry, not with respect to h, with respect to x. What is the integral of 2x with respect to x? This is plus x squared, plus an integration constant. Now, before I write out this constant, let's think about what an integration constant is saying. When you integrate, when you are computing an antiderivative for a function, right, of a single variable, including the constant is a way of saying, well, you know, this thing that I found, so for instance, the integral of 2 to the x, or not 2 to the x, 2x. The integral of 2x is x squared plus c. And the reason why is because if I'm saying the antiderivative of 2x is x squared, that's not the full picture, because someone else could say, well, what about x squared plus 5? Right? Like x squared plus 5 is also a function such that when you take its derivative, you get 2x. So it's giving you the full picture, right? So similarly, I could write constant here, and you might be happy there. But remember, this is a function of two variables, right? And I have just integrated with respect to only one of them. So I've integrated with respect to x. So with respect to x, the most general possible constant that I could write out is not just an actual constant. It is a constant in the sense that we treated y as a constant. And so the most general possible constant, right, to think of here is a function of y that I called little h. Now, if you don't believe this, let's take the partial derivative and check that it matches up with this. So if I took the partial derivative with respect to x here, what would I get, going term by term? E to the xy plus 2x plus 0. So I get exactly that. Okay. So this is the thing that I have to remember. Now there's a quick check that we'll do going through this process that will ensure that what you do always works out. So this isn't, you know, there's multiple ways of checking your work while you're going along, basically. Okay, so this is what I get. Now what I want to do, and here's why it doesn't matter what order you do this in, because you're going to be using both of these equations anyway. So what I want to do is I want to take this expression and plug it in to the second equation. So 2y plus e to the x is equal to the y partial of h. That's just me recopying this equation backwards. But also, the y partial of h from this is equal to what? So now I'm going to take the y partial of this thing. So the y partial of this is, so the y partial of e to the xy is just e to the x. The y partial of x squared is 0. The y partial of little h, since it's a function only of y, is the full derivative of little h with respect to y. So h prime of y. The e to the x's cancel. And so what I'm left with is little h prime of y is equal to 2y, which is something that only depends on y. Now, what I said earlier about the check, here it is. When you do this process, okay, you get to this step. If you've done everything correctly, at this step, you should have little h prime of either y or x, and then something that depends only on the variable in question. Okay, so there should be no x's showing up in this case. If I had done this in reverse order, and I'd found a little h of x instead, this should be little h prime of x is equal to something that only depends on x. So you'll be able to tell at this step whether or not something you've done is completely off the wall. Okay, so here we go. And now how do I find little h from this? I just integrate with respect to y here. So this is so little h of y is y squared, right? Plus c, if you like, that doesn't matter too much, okay, because that's going to get absorbed here. And so what do I get here? Well, then h of xy is e to the xy plus x squared plus y squared. Right, plus c if you like. So I'm going to absorb the c with the other side c. So then h of x, y equals constant should do it. Right? This should solve my differential equation. Now, I'm not totally done here, so I'm going to set this equal to constant, but I'm going to impose my initial condition. So let's impose my initial condition. Let's remember what this thing was in the first place. So the differential equation is this thing, and y of 0 is 0. Imposing that initial condition, I get e to the 0 times 0 plus 0 squared plus 0 squared is equal to constant. And so constant is equal to 0 here. And so what this equation becomes is e to the xy plus x squared plus y squared is equal to 0. Okay. So let's rewrite this. This is what I get. Now, in this case, I can actually go further. This is not always something I can do, but for this particular example, I can go further. I can actually find an explicit solution here. Notice, this is a quadratic in y. Right? This is a quadratic in y. And so by the quadratic formula, y is minus, this is minus b, which is e to the x here, plus or minus the square root of b squared, which is e to the 2x, minus 4ac, which is 1 times x squared, so minus 4x squared, all over 2 times 1. Now, technically, this is two different families of solutions, but if I want the initial condition to be satisfied, then I need to take, since this is minus e to the x, I need to take the positive root, or it won't be satisfied. So to satisfy initial condition, y of x is taken to be minus e to the x plus square root of e to the 2x minus 4x squared, right, all over 2. So here is my solution. Now, you can't always do that. You can't always go further. Sometimes you're just happy stopping here. So typically, where this problem ends is an expression like this. Okay, usually you're happy with that. In this case, though, I just wanted to show that we could actually go further and get an explicit solution. So it's not that an explicit solution is impossible for these problems. Okay, sometimes it's possible, but typically it's not. And figuring out, like, there's no real general way to say whether or not an explicit solution is possible. That entirely depends on whether the thing in question can be solved in this way, like whether or not it has some nice inverse showing up nice enough to be able to solve this expression. It's not always the case. Okay. All right. So this is an example of how to do this. Now, if you really, really wanted to check this, right? Like, what would you do? You would take that expression and you'd say, okay, if I take that y and take its derivative and add to it e to the x times y plus 2x all over 2 times y plus e to the x, I should get 0. I'm not going to check that for you, but you maybe should check that for yourself to make sure that it actually works and that this is actually a solution. Okay. Let's do one more example of this before I have to talk about tomorrow kind of a complication here, which is basically what happens when the exactness condition is not satisfied. So we'll see what happens, that we're not totally out of luck, and that there is, on occasion, something that we can actually do to fix that issue. So let's do another example, though. Okay, so let's find an implicit general solution to the equation that is xy squared plus y plus e to the x dx plus x squared y plus x dy is equal to 0. Okay. So here is my m, right? This is my m of xy. Here is my n of xy. First, I check exactness. Okay, so let's check exactness. What is the y partial of m here? Well, this is xy squared, so the y partial here is 2xy plus 1, because the y partial of y is 1, plus the y partial of e to the x is 0, so 2xy plus 1 is what I get. What is the x partial of n? Well, it's 2xy plus 1. So the exactness condition is satisfied. Now, on these problems, even if I don't tell you to check exactness, you have to always check exactness. Like that's the first step every single time, because as we'll see, if it's not exact, there's something extra you have to do first, okay, that makes the problem significantly longer. So the question of whether or not it's exact is extremely important, and that's something that you have to address immediately. So immediately you have to figure out whether or not this thing in question is exact. Okay. All right. So let's see. What do I do now? So now I set up the differential equations. So the partial differential equations, the x partial of h is equal to m, and the y partial of h is equal to n. Right. So I set up this system. Okay, where m is xy squared plus y plus e to the x, and n is x squared y plus x. Okay. All right, so again, it doesn't really matter here. Maybe this is a little bit simpler, but I'm still just going to take this first thing here. Okay, and I'm going to integrate both sides with respect to x. Okay, so I'm going to integrate both sides with respect to x. So if I do that, what do I get? So maybe I'll put this first one here. So what do I get? So h of xy is equal to here, so if I'm integrating this with respect to x, each term, this would be 1/2 x squared y squared. If you don't believe yourself, just check that the partial derivative of this with respect to x is xy squared. So if I'm taking the partial derivative with respect to x, this is 2 times 1/2 times x times y squared, so it's x y squared. Yeah. If I integrate y with respect to x, I just get xy. And e to the x with respect to x is just e to the x. Plus some unknown function of little y alone. Again, once you get to this step, you can just verify for yourself that if you take the x partial here, you should get xy squared plus y plus e to the x. You do. Okay, you do, because that's 0. This would be xy squared. This would be y. This would be e to the x. So that's what you get. Now I want to plug this into the second equation, just like before. I want to plug it into the second equation. And so x squared y plus x, that is the y partial of h. But then this is also equal to, now I'm going to take the y partial of this quantity. All right, so I'm going to take the y partial of this thing. So taking the y partial, this is x squared y. From taking the y partial of this term, y partial of this term is just x. Y partial of this term is 0. Y partial of this term is h prime y. Notice x squared y plus x cancels from both sides, and I'm left again with an expression that only depends on y here. Of course, y doesn't even show up. So if h prime of y is equal to 0, this means that h of y is equal to constant. Okay. And so my implicit general solution is h of xy is equal to constant, or written in another way, 1/2 x squared y squared plus xy plus e to the x is equal to constant. Right? I absorbed this constant into the right-hand side constant, right? Okay. All right. So this is another example of what to do solving these. Now, I will lead into what it is we want to do if this thing is not exact. Okay, but I won't do an example until tomorrow because I'll run out of time otherwise. So, if this is exact, this is how the process goes, okay, with very little deviation. So then the question becomes what to do if this thing is not exact. All right, so suppose I have the equation m dx plus n dy is equal to 0, but the y partial of n is not equal to the x partial of n. What do I do? Unfortunately, this process that we relied on before just won't work. In fact, if you try to make it work, you will get to a variety of logical contradictions or circular arguments, circular computations that you make where you're just not able to finish it if you're doing everything correctly. So that's not good. That's not optimal. Right? That's not going to get us anywhere. So what do I do here? The idea, I believe Euler was the one who originated this idea. The idea is to use an integrating factor. this relates to the integrating factor that we mentioned way back with last week with linear equations. So this is basically the same integrating factor, just slightly dressed up. So it is slightly different, but you will see how it applies to that linear case. So the idea is to use an integrating factor rho of xy. So what does this idea say? The idea is that suppose I have an equation like this. Okay, suppose I have an equation like this, and I take some non-zero function rho of xy, and I multiply both sides of this equation by rho, so that I get rho of xy times m xy dx plus rho xy times n xy dy is equal to 0, because multiplying rho by 0 is 0. The question is, how does this alter the original equation that I started with? Well, it turns out, right? It turns out that if I call this asterisk and this original one star, it turns out that asterisk and star have the same solution sets. Again, we want rho to be non-zero. I'm not talking about multiplying both sides of an equation by 0. That's stupid, right? So these two things, right, have the same solution set. All right. Well, how does this help us, though, right? So if I started with an equation that looks like this, and now it looks like I have made that equation more complicated by multiplying by some function of rho of xy, how does this help me? The idea is maybe this is exact, right? So maybe star, or asterisk, I'll say, is exact, even if star is not. Well, how would I check whether or not it's exact? Well, this would be like my new big M, and this would be my new big N. So what would need to happen? Well, the y partial of rho of xy, M of xy, needs to equal the x partial of rho of xy, N of xy. But what does that mean? I need to use my product rule for partial derivatives here. So I have two functions, both x and y here. I need to take the y partial and x partial of this product. So there's a product rule. So there's the y partial of rho times m plus rho times the y partial of m. That's the left-hand side, sorry. And that's equal to the x partial of rho times n plus rho times the x partial of n. If this equation has a solution, then the y partial of this thing is equal to the x partial of this thing, and this thing is exact. So if this has a solution, then asterisk is exact. And once it's exact, well, now we know the process for finding an implicit general solution. Right? So we're good. But how do I know if this has a solution? This is a PDE, right? This is a first order PDE, which is not something we talk about how to solve in this course. If you want to know how to solve this, you're going to have to take Math 462. Right? So Math 462 will give you various ways of solving first order partial differential equations. One's called the method of characteristics. It's a really, really cool thing, but unfortunately it's not something that we are going to get into in this course. So how do I deal with this? Well, I'm not always guaranteed to be able to deal with this. Okay, so one, maybe kind of like the first thing. One, I can't always solve this. So sometimes you're just screwed. There's nothing that you can do. Here, you can't fix it, and the equation, you just can't do anything with it. But sometimes I can solve this. Either, well, I should say, sometimes I can solve this either, maybe I should say directly, in a way that is suitable for this course, by assuming that rho is of a simple form. Now, this just isn't always going to work for all equations, but sometimes it does. So I can assume rho of xy is actually just a function of x, or rho of xy is just a function of y, and sometimes this works. Now, in this course, this is always going to work whenever you would need to do this, because I'm not going to be so mean to give you a problem that leads to nowhere. So you can't always solve this, but you can assume that maybe rho actually only depends on x and y. Why is that important? Because if rho only depends on x, then the y partials of rho are going to be 0. So for instance, this term would be 0. And if rho depends on y, then the x partial of rho would be 0. So this term would be 0. Now, how would you know which assumption to make? You'll know which assumption to make based on which assumption makes this equation easier. So if m is some big nasty thing, but n is relatively simple, then you would want to assume that rho is a function of x, so that this term becomes 0. Similarly, if n is really nasty and m is nice, you would want to assume that rho is a function of y purely, so that that term is 0. So this would be up to you, but it's important that you understand what it is you're doing, what assumption you're making, and why. Okay? And once you've done this and solved this equation, we'll see how, if you make that assumption, this turns into a first-order linear equation. So with this assumption, this equation is a first-order linear equation. So this is where the integrating factor terminology comes from. Because rho is going to be a solution to this first-order linear equation, which means that it is itself going to be an integrating factor, right, in the sense of linear equations. Okay, first-order linear equations. All right. Anyway, so that's where we'll pick up tomorrow. So I'll do a couple of examples of this tomorrow, and then I'm just going to go straight into doing just general review of Chapter 1 tomorrow. So by the end of tomorrow's lecture, I should be totally done with the Chapter 1 material, and we'll go on from there. So as I said earlier in the comments, I said that I would host office hours this Wednesday, so I'll let you know about those later. All right. So anyway, that's it for now. So I will see you all tomorrow. Remember, you have homework due tonight, so have a look at that on Elms. So anyway, see you all later.